Hey folks, welcome back. In this video we're going to go over question 4 from the 2024 SQA Advanced Higher Physics exam paper. So let's get into it. Question 4 says the Double Asteroid Redirection Test DART was a recent NASA mission. It was designed to crash a spacecraft into an asteroid to deflect the asteroid from its path. This was a test to see if a spacecraft could deflect an asteroid that is on a collision course with Earth. The target of the DART spacecraft was the asteroid Dimorphos, which is in a circular orbit around a larger asteroid Didymos as shown in figure 4a. So there's the larger asteroid Didymos and the smaller asteroid Dimorphos which is orbiting around it. And then we've got the DART spacecraft heading towards Dimorphos. It then tells us the radius of orbit of Dimorphos is 1.2 times 10 to the 3 meters and the period of orbit of Dimorphos is 11.9 hours. Part A says calculate the mass of Didymos and there's 3 marks available here. Well, since Dimorphos is a satellite of Didymos, we can use satellite equations here. And we can firstly say that since the gravitational force of attraction provides a centripetal force on Dimorphos, we can write that Fg equals Fc, where Fg is a gravitational force and Fc is a centripetal force. So equating these two forces, we have gmm over r squared is equal to mr omega squared, where we're writing the centripetal force in terms of the angular velocity omega here. We can then cancel the m's on both sides, so we have gm over r squared equals r omega squared, and we can then write this as gm over r squared equals r times 2 pi over t squared, since we have from the relationship sheet that omega equals 2 pi over t. Or if you prefer, you could actually just start off straight away by saying gmm over r squared is equal to mr 2 pi over t squared, which is using some of the satellite equations from the relationship sheet. We can then expand this right hand side and rearrange for the mass m, so doing that we would have r times 4 pi squared over t squared, and then we'd have to multiply up this r squared term and divide both sides by g. So we end up with m equals 4 pi squared r cubed over gt squared. And then we're in a position to substitute the numbers in, so we have 4 pi squared times 1.2 times 10 to the 3 cubed divided by 6.67 times 10 to the minus 11, which is our universal constant of gravitation from the datasheet, times 11.9 times 60 times 60 squared, where what we're doing there is converting the period of 11.9 hours into seconds. So you have to do 11.9 times 60, and that term is squared. So putting that into your calculator should give you an answer for m of 5.6 times 10 to the 11 kilograms. Part B says the mission was planned so that the impact did not knock Dimorphos out of orbit around Didymos and put it on a collision course with Earth. Part 1 says calculate the escape velocity from Didymos at the orbit of Dimorphos, and there's 3 marks available here. Well, writing down what we know from the question, we're trying to find the escape velocity via escape. We know that g, the universal constant of gravitation, is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared from the datasheet. We've just calculated the mass of Didymos, which is the larger asteroid, to be 5.6 times 10 to the 11 kilograms. And we know the distance between the two, i.e. the radius, is 1.2 times 10 to the 3 meters. So writing down our equation for escape velocity, we have v escape equals the square root of 2gm over r. Substituting in the numbers gives the square root of 2 times 6.67 times 10 to the minus 11 times 5.6 times 10 to the 11 divided by 1.2 times 10 to the 3, and putting that into your calculator, remembering to use the square root, should give you an answer of 0.25 meters per second. B part 2 says the DART spacecraft collided with Dimorphos, which resulted in the period of orbit of Dimorphos around Didymos decreasing by 30 minutes. Explain fully the change to the gravitational potential energy of Dimorphos as a result of this collision. And there's 2 marks available here. Well, we can firstly say that since the period t decreases, the orbital radius r decreases. In other words, it takes a shorter time to travel a shorter distance. Therefore, we could say the gravitational potential energy is less or more negative since EP is proportional to negative 1 over r. So if the denominator r is smaller, that gives us a bigger EP, but because of this negative sign, that would mean it's less or more negative, you could say. And this just comes from the equation for gravitational potential energy on the relationship sheet, EP equals minus gmm over r. Lastly, part C says asteroids on a potential collision course with the Earth must be impacted at a large distance away from Earth. Suggests why this impact must occur at a large distance in order to prevent a collision with Earth, and there's 1 mark available here. Well, you could say one of several things here. You could say the collision only results in a small deflection, or a large distance is required for a change of trajectory greater than the diameter of the Earth, or a large distance allows more time for the deflection to affect the path of the asteroid. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.